All right, so this assignment right here, this lecture is gonna talk about how to using a velocity versus time graph, how to predict what the displacement graph is and what the acceleration graph is. It's not going to be 100% accurate sometimes because of flaws in the graphs, and I'll try and point that out as we go. But the basic idea of these assignments is that when you go from velocity to displacement, like this arrow here, that let me see if I can make that a little bit better. That we are going to take the area of the velocity versus time curve, and when we take the slope, we can go forward to acceleration. And this is this is generally true too. So meaning you could take the area of, say, acceleration and go backwards to velocity. Or you could take the slope of displacement, or, well, this is technically position, right? Position versus time, and go backwards to velocity versus time. And what I was saying there about this graph is I don't really care for it saying displacement. It should really say position. However, when we take the area, we are getting the change in position. I've tried to mention that a few times. So this is kind of the general idea. We won't need to do this right here, right, and go from displacement to velocity or go from acceleration to velocity. But we will do these two on the right here. We will go backwards to get area and forwards to get slope. Or I should say that again, we'll take the area to go backwards to position and take the slope to go forwards to acceleration. All right, so let's start off by doing some areas, and let's go ahead and divide, because really we want the area between the x-axis and the curve, right? So the area we're interested in is all of this, which I'm going to shade yellow. All of this above or under the curve and above the x-axis, and all of this below the curve, or below the x-axis and above the curve. So we're interested in all of that yellow area. So we have to divide that into some shapes that we can handle, right? Because obviously we can't deal with all of these shapes. We don't have nice formulas for them. So let's go ahead and divide, let's call this first triangle right here a shape on its own. So one of the things that I'm going to do to make this problem easier is work in set chunks of the graph that make the most sense. Meaning that if I go back for a second and get rid of this triangle I just drew, and get rid of the yellow, I guess, too. Let's see if I can put that back in. All right, so you got the yellow area right there. Meaning that when we take the area, we could have started with this triangle right here, which I'm going to color brown. All right, and that would just be from 0 to 10 seconds of the velocity versus time curve. The reason I don't start with that is because I don't know the height of that triangle. It's not easy for me to see. It looks like it's about 5, but I don't know for a fact. So I'm going to go ahead and take the area of this entire brown triangle, which looks like it goes up to a height of 10. It's just much easier to work with, and so that's what I'm going to do. Going to the next part, I'm going to go from 20 to 30 seconds and say that, because this is just a lot going on right here, right? I'm going to say that this is a triangle right here that I can take the area of. And this is a square or rectangle right here that I can take the area of. Why didn't I guess a good question is, why didn't I take a longer rectangle? For instance, let me see if I can draw this maybe in black here. Why didn't I take this rectangle right here, going across the bottom? The idea here is that I want to work in chunks of time. So meaning I'm interested in chunks of time that go in order and that take reasonable amounts of area that I can think about. So meaning either I take the 20 to 30, right, and just work off the purple part, right, off these purple lines. Let me see if I can go ahead and add those back in, which I can clearly see as a square and a triangle. Or I take the 20 to 50, which I'll show you what that looks like. I take the 20 to 50, which would be this. But that's harder for me to deal with because then I have to split all of that up. And I also lose some detail, right, in the graph, meaning that there's different slopes in there. The graph is doing different things. So I really want to go smaller chunks that are reasonable. It's kind of the idea here. It's kind of, we're trying to pick the best way to create this graph, which is going to be smaller chunks that are reasonable. So I like the 0 to 20 chunk of that brown triangle. Could have went 0 to 10, but then the problem would have been had I just gone 0 to 10, let me show you this. I would have been left with that for 10 to 20. And I don't know what the heck that is, right? That's almost like I'd have to do more math to figure that out because we're missing that white triangle right above it. And yeah, I don't really know. So I like trying to take easy chunks, but small chunks at the same time. It's kind of the best way I say it. I always get students that want to take too tiny of chunks. They want to take areas of shapes that are too small. Just be careful with that. Try to make your life easy, right? Take small shapes, but go larger if it makes sense. So I think doing an example will help the most. All right. So here we got this area right here that we're going to take from 0 to 20. Let's go ahead and get the area there. So what we can say then is that the area of that triangle, right, is equal to 1/2 the base times the height. And if we go back up and look at that, it looks like the base is 20 seconds and the height is 10 meters per second. Now we know that by finding the area of this triangle, we are finding a change in position, a displacement. So that was why our graph up here originally said displacement versus time. I still like calling it position versus time, but what we're finding with the area is displacement. Okay, 20 times 10 is 200. 200 times 1/2 is 100. And this is going to be 100 what? Well, if we look at the units, we see that the seconds cancel, so we're saying 100 meters. All right, so what this means then is that the change in position, right, between 0 and 20 seconds is 100 meters. So this is the delta x from 0 to 20 seconds. 0 seconds to 20 seconds. Okay, so that's kind of what we're saying here. So what we can now do is go up to our displacement graph. See, I'll probably use this blue. We can create a point at 0. We have to assume a start location. And a lot of times they say, they'll say something at the top of the graph right here where I'll write my name. Assume that let me see. Assume at time equals 0, x equals 0. That, let me see. I don't want to write it like that. We'll just say, we'll assume that xi is equal to 0 meters. And that's kind of what we're doing here. So, all right, let me go ahead and get that blue pencil back. All right, so we're going to go from 0. We're going to go have a displacement here, a change in position from 0, 100 in the positive direction, right? Because this area of this triangle is positive 100 is what we figured out there. So we're going to go forward 100. Where's 100? 100 would be right here. And notice where I'm drawing this dot. It's at 20 seconds, right? Because we're going to hit positive 100 if we start at 0, because our displacement is positive 100. So we'll hit position 100 at 20 seconds. At time 0, we were at 0, position 0, because they told us that we can assume this, right? All right, so anyways, coming back to the graph now, let's get the next area or chunk here. Let's go with this bright green. Looks like we can see a triangle right here. I'm talking about the chunk will be between 20 and 30 seconds. And we have also, I'll just do this. Also have this square or rectangle right here. So we have this one. I'm trying to show you the square rectangle, and then this triangle up here. All right. So I want to take both of those areas here. All right. So for the top triangle, right? Go ahead and draw a line there. For the top triangle, we have area equals 1/2 base times height. Just writing it out. Equals 1/2. Base is 10 seconds. Height is, what is the height of that triangle? We have 30 minus 20, right? If I highlight that in yellow, the height is just, if you can see that, just right there. It's kind of hard to see, but it's 30 minus 20 for the height, right? Just of the triangle. All right, so we're going to say 30 minus 10 is 20. So we have 20 meters per second. Once again, watch those units. They can cancel. And we're left with pretty much the same calculation we just did a second ago, although slightly different. Okay, so half of 200 is 100. So we're saying that although it looks a little different, this triangle above here also has an area of positive 100 meters, right? Okay, and then this square or rectangle right here, right? Let's get that area next. So that area is going to equal to base times height, which is equal to the base is 10 seconds. The height is from 0 to 10, so 10 meters per second. We can go ahead and cancel off those seconds, and we're left once again with 100 meters. Notice these are all positive, right? And that means our delta x, right, from 20 to 30 is going to be these two added together, this positive 100 and this positive 100, right? Because we have to think about both areas. They happen at the same time from 20 to 30, both those displacements. So that means so what we're saying is the delta x, right, from 20 seconds to 30 seconds is positive 200 meters. Now, this does not mean the object goes to 200 meters. That's incorrect, right? That we're not saying its final position is 200 meters. We are saying that it changes its position by 200 meters in the positive direction. So where was its initial position? Well, it didn't start at 0 this time, right? Between 20 and 30, where did it start? Well, it started at 100. So it's going to go forward 200 meters by 30 seconds. 100 plus 200 would be 300. So we're saying about right there. And notice I put that dot at time 30. And then we can just connect the dots here. We don't have to be too concerned with is it a curved or straight line, but we're just trying to get a general sketch here. I always like to write the numbers above the dots because that reminds me of where that object is. And sometimes that gets a little crazy with the graphs, so it's nice to have that reminder. All right, so let's go ahead and go to the next part. Once again, another difficult shape to deal with. Looks like we got multiple shapes here. So I'm thinking for this one, let me grab, let's go back with brown again. So with this one, we have this triangle right here at the top, which you can tell is kind of sketchy, right? The graph almost looks like it's poorly drawn because it is. There's a couple ways to handle that. I think for this case, because we're going to handle it this way for this case. We're going to pretend that graph actually looks a little bit more like that. And that's just going to make our life easier. I think it's just a typo based on whoever made this graph originally. So we're just going to deal with it like that. So that's much easier to deal with, that triangle right there. We're then going to find the area of this. Let me see if I can. Let me see, I can do better than that. Let's go with. Let's go this way. Let's go horizontal and vertical. All right, and so that that rectangle right there. Okay, so let's go ahead and get those calculations. So the first one, let's do the triangle. The triangle is area of the triangle is equal to 1/2 base times height. I just won't write I'm not going to keep writing that formula. It's so simple. The base is 40 minus 30, right, for that tiny triangle up top. So the base is going to be 10 seconds. The height is going to be, looks like 10 meters per second as well. Okay. So we know the seconds will cancel. Whoops, seconds will cancel. We can go ahead and say that this is equal to half of 100, which is 50 meters. Positive again. Let's get the area of the rectangle, which is equal to base times height. I said I wasn't going to write that. I'm just going to say it and then plug numbers in. All right, so base here is once again 10 seconds. Make sure and double check if you don't understand where that's coming from. Height there is 20. I think everybody can see that, right? This base, let me get my highlighter. This base right here. Dang, that's just not coming through really well. Let me try bright green. All right, that's a little bit better. That base is right there, is just 10 seconds, and the height is right here on the side, and is equal to from 0 to 20, so it's 20 meters per second. So we're talking about this, putting a little green in here now with this brown. All right, so that rectangle right there. So we're going to go ahead and get that. Let's go ahead and cancel our units. Seconds go away. We can go ahead and multiply. 20 times 10 is 200 meters. All right, so in that time period, then we travel 200 plus 50, which is 250. Go ahead and draw another line there. So we're saying from 30 to 40 seconds. Let's go ahead and get the blue. So we're saying that this right here is 250, right? From 30 to 40. Okay, so we're going to come up here from 30 to 40, add 250, which is our change, right? Because this is a positive 250 to 300. We're not going to 250. We're increasing our position by 250 because it's a positive 250 to the right. And so we get to 550. 500 is between 400 and 600, so a little bit above that, maybe about right there, right? We'll call that 550. All right, so far so good. Let's go ahead and do the next part, which is going to be this shape right here, which we already know, right? We just did that, and we said that that was equal to positive 200. So let's go ahead and add that on. 550 plus 200 is 750. 700 is between 600 and 800. A little bit above it is 750. So we're saying about right there. All right, that's good. Then we'll get this triangle next. Now this one, we're not going to, I'm gonna make this blue. We're not going to assume that it's hitting right at 60 because it's not. It clearly isn't. And so this one we're gonna deal with. And we'll go ahead and get the area here. Now the base of this is gonna be from 50 to 58. So about, right? So we'll go with 58. Sounds good. So it's gonna be an 8-second base. The height of this blue triangle is going to be 20 meters per second. So let's go down here and get this area here. So we're saying the area of this triangle is equal to 1/2 8 seconds, right? Times the height there, which is 20 meters per second. I think it was 20. Yeah. Yep. All right. So once again, cancel those units off. Probably my favorite thing to do is cancel away units. I don't know why. But anyways, all right. 20 times 8 is 160 times 1/2 is 80. So we're saying that this is equal to 80 meters. Once again, positive. So 8 looks kind of weird. All right. Positive 80 meters. So we're saying that this blue triangle is positive 80 meters. Okay. So then coming up here, we can go ahead and add that on. We get the blue again. So 750 plus 80 is 830. 800 is right here. This is at, so this is going to be 800, yeah, plus, so 830. Okay, so 830 right about, now I have to be careful here, right? Because it's at time, I'll put it right there. Yeah, slightly above the 800 line, right? So we'll call that 830. And once again, it's at time 58 seconds. So this is important because it's not right at 60 there. All right. And it's also important because what we're about to see is that this is going to be a relative maximum. Well, it's going to be a maximum, not even a relative one because there's no other maximum. There's no other thing. There's no other maximums. So this is just going to be a maximum for our graph. And the reason being that now the slopes or the areas that we're going to start taking are going to be, let me find another color here. I'm going to go purple, are going to be negative, right? So the next area we're going to take is from 58 to 70. So this will be a 12-second base. And I'm going to take this entire triangle, right? I said take small chunks, but make your life easy. And when you can, like this, and take a larger shape. So that's what we're going to do here. So we'll go from 58 to 70. We'll take the height of this purple triangle and the base of this purple triangle, 1/2 base times height, and find the area there. So let's go ahead and calculate that. So I'll draw another line here. The area of this triangle is equal to 1/2. I think we said the base was 12 seconds, right? Because it went from 58 to 70. What about the height there? Looks like negative, what is that? Is that from 0 down to negative 30? Okay, yeah. All right, so negative 30 meters per second. Okay. 30 times 12 is 360. 360 times 1/2 is 180, but it's negative, so we're saying a negative 180. So it's saying here that the object displaces 180 meters to the left. So not that it goes to 180, right? So we go back up to our chart here. I can label this really quick. Call this negative 180. And then you can put an M there too. Let's go ahead and we got to go downwards from 830, 180. So if we go downwards, or not down, well, left or down, whatever, we gotta go in the negative direction. That's what I'm trying to say. So if we go in the negative direction from 830 by 100, that's 730, minus 80 is gonna be 650. All right, so we're gonna get the 650 by time 70 seconds. So 70 seconds is, or 650, we'll find that is about 700's halfway between, so 650 is about right. I have a hard time drawing dots for some reason. Okay, it's about right there. once again, I'm going to label it because obviously it's hard to tell, exacts there with this curve. So we got about 650 being right there. Good. We got one more shape left, and then our graph is going to be done. Okay, once again, another negative area. This time, it's this easy rectangle here. Base is going to be 10 seconds. Height's going to be negative 30. So we're saying, I'll go ahead and do the math, even though it's kind of obvious. Ooh, we got blue. Trying to black. Okay, area is equal to 10 seconds times negative 30. Cancel my seconds. Forgot to do that above. Cancel my seconds. And we're going to get negative 300. Okay. So go ahead and write that in. I just do that because it's just to show you, just so we're on the same page. And then once again, 650 minus 300 is a little easier. Gives us 350. So that's going to be our final position at time 80 seconds. 300 is about right in the middle, so a little bit above, maybe about right there is going to be 350. We'll just complete the graph there. All right, so there's our position versus time curve for for this object. It's that simple. Kind of a little bit of a pain though, right? But it's cool that you can predict the graph from the velocity versus time curve by using area. All right, so now let's use slope and go the other way and make the acceleration versus time curve. All right, so what slopes do I have here, right? And this is probably a job for the highlighter. Let's see, maybe in red. And yeah, we'll try red. Why not? So what I'm seeing here for slopes, if I just go through this, positive slopes I'll make red. It's not, that red just doesn't really pop really well. Let me make it a little larger. Maybe that'll be easier to see. Okay. All right, so there's a positive slope right there. Here's another one right here. We're looking for any up and to the right slopes. So I guess there's only two. Let me differentiate those two a little bit here. Let's use yellow. So I'm going to erase this red one right here and make this, whoops, like I'm erasing everything. Geez Louise. All right, this one right here is yellow, is different than the red one. Those are both going to be positive slopes. And they're going to be different, right? So I'm going to have to find the slopes of both of those individually. And then I'm going to have to find the negative slopes and the zero slopes. But let's start there with the first two. So once again, we're kind of breaking this up into chunks. So I'm going to work with the red slope first, then the yellow slope next. And then we'll go forward from there. So let's go ahead and get that red slope. So for our slopes, I'm just going to grab endpoints, right, to find these values. So I got time for the red slope, 20 to 0 seconds. I got height there of 10 meters per second to 0. So what I'm saying here is this, right? We're taking advantage of this formula right here. Acceleration is equal to VF is equal to, let me write it all out so it's clear where this is coming from, is equal to delta V over T, right? But what I said that sometimes we like to write the delta T, and this is one of those cases. All right, so we're going to then split this up into VF minus VI over TF minus TI. Okay, and now we're just going to plug in values. I always start with the times first because time's always going to be positive when you subtract the two, and it's just a little easier. So I always like to make these problems easier for myself whenever that's possible. Not 10 on bottom, that's going to be 0, the initial time. All right, so because we said for the first triangle, we're using that larger chunk, right? You remember that. Final velocity is going to be positive 10. Initial velocity is going to be 0. We do the math here. We get 10 meters per second per 20 seconds, which is equal to positive 0.5 meters per second, or meters per second squared. Okay, so that's my first area. So then I'm going to come down here to this, or first slope, sorry. Then I'm going to come down here to the acceleration graph, right? And I'm going to pick a color here, maybe orange. And what I'm saying is for the first 20 seconds, right, we should see this orange line right here. Now, one of the things that, that we can do when we make this graph is use open circles right here at 20, and the reason being, and I guess by that means you could use a close, or should we use an open at the beginning too? Yeah, I'm gonna use it anyways at the beginning too. All right. The reason I'm using open circles is because I don't know what is going on at 20. Meaning, is it part of the red slope or is it part of the yellow slope? This is tricky, right? And in math class, we would say that the acceleration is undefined at 20 seconds. We don't know. We don't know which slope it belongs to. And so real objects don't move this way. We know their acceleration all the time. This would be more of a curved line. It wouldn't be as straight and pointy, because when it's like that, it's easier to work with. But the problem is that that's not reality. So anyways, these open circles just say we don't know the acceleration at that point. So at 0.5, you have this straight orange line, but with the circles on the end being open, saying we don't know the slope at that point. All right, so, okay, good. Let's get that next slope, that yellow slope, and it looks a little steeper. So let's go ahead and move back down here. So this is from, I think, 20 to 30, right? So we're doing the same thing as before, VF minus VI over TF minus TI. And we don't have to write that every time. If we remember it from above, that's fine. But you should definitely always write your numbers. And I wrote the wrong number. It should be 30 seconds minus 20 seconds, right? And I should probably go up and double check that. So we're going from 30 to 20. Velocities are going from 30 to 10, right? And confirm that with yourself. Make sure that that's what you see for final initial velocity. All right, so we have 30 meters per second is our final velocity, and 10 meters per second is our initial velocity. And remember, this is relative to those times, right? 30 lines up to 30 seconds. The 10 lines up to 20 seconds. So 20 seconds is our initial. Remember, initial can be whatever you want it to be as long as it occurs before the final. And the same is true with the final. It can be whatever you want it to be as long as it occurs after the initial. This makes our formulas way more versatile, and they can be applied to a lot of different situations. All right, so let's go ahead and do the math there. Looks like we got 20 on top divided by 10, which is going to equal 2 meters per second per second. Okay, and that's going to be positive. So now we're going to add in that slope right there. Grab that orange marker. All right, so we're saying a positive 2. Okay, this is kind of rough because this is going to be off the chart a little bit. Just only had so much room on this page. So once again, I'm using those open circles, and I'm connecting them by a bold orange line in between. And you can see that lines up to positive 2 over on the y-axis, right? That's positive 2 right there. Okay. All right. Let's go ahead now and go to the next one, 30 to 40. So now we're going to be dealing with the negative slope, right? Let me grab another highlighter here. Let's make this a highlight in blue, and I'm saying this slope right there. All right, so let's go ahead and get that one. 40 minus 30 is going to be our time change, and our height is going to be 20 minus 30. So I'm saying this time we're going to have on bottom 40 seconds minus 30 seconds. And I think I said on top it's going to be 20 meters per second for my final minus 30. Okay, so in this case, we're going to get negative 10 on top, positive 10 on bottom, which is going to equal negative 1 meters per second per second. All right, draw a line there, a line here. Let's try and keep these separate. So, so we're saying that that slope is -1 meters per second. Let's grab our orange marker here. -1 is down here. So we're saying from 30, I'll make some circles, to 40 with a line connecting them. And we're saying it's going to be right there at -1. All right, and then this is the best one, the nicest ones to take. This flat line. What's the slope of this flat line? Everyone should be saying it or know it. What's the slope? I'll make it pink here. What's the slope of this line? All right, everyone should be saying 0. Okay, so that's awesome. Let's go ahead and draw that in then. From 40 to 50 seconds, our slope is, or our acceleration is going to be 0. Okay. Now, the next one's a little trickier, right? And I'll make this, we'll go with orange here. So this orange slope right here is we're actually going to use all of that, right? And you might say, well, it drops below 0. Doesn't matter. It's a negative slope the whole way. It's a constant negative slope. Let's go ahead and find that total slope from 70 to 50 seconds, right? So from 70 to 50, and this deals with that obnoxious 58 seconds in there too. So let's go ahead and calculate this. It should be negative. Looks like my final height at 70 seconds is going to be -30 and +20 at 50 seconds. So, so we're saying 70 seconds minus 50 seconds. Whoops. Trying to go too fast here and making mistakes. Acceleration is equal to that. And at 70 seconds, we are at -30, and at 50, we're at +20. Okay, so that's going to give us a -50 on top. And on bottom, +20 seconds. This is going to give us -5/2, which is -2.5. All right. So what's rough about that? Well, this graph isn't really labeled for a -2.5, so I'm just going to add that in right there. Let's go ahead and get that orange marker here. So we're saying from 50 to 70. Once again, open circle at 50 all the way to 70. We'll have another open circle. And then finally, the last segment, let's use the highlighter again. Let's go, I don't know, let's go pink again for this because this is the 0 slope just like it was before. All right, so the slope of that pink line right there is 0. So we'll add that in with orange down here from 70 to 80 seconds. Open circle, it's at 70, and open circle at 80. All right, so that's what I'm looking for there for the acceleration graph. Why the jumps, right? Well, what about the connected parts? Well, there's 2 ways you can deal with that. In math class, you can just leave it like this, and this is probably the best way. The other way of dealing with it is to draw dotted lines right there. So it kind of, I don't know, sometimes people like looking at dotted lines. It feels like the graph has more structure. But what we can see is those dotted lines, those are where we can't know the slope. Those are the undefined parts of your graph. And so that's what's going on, that's what's happening, and that's why. So anyways, yeah, hopefully that makes sense, and hopefully you're okay with that. All right, so what next here? We are almost done. We got one last thing, and that is up above, right? We have this grid up here above, and I think it seems kind of tough, but I think the easiest way to deal with this, because you can look at maybe acceleration or displacement to figure this grid out up here, but I think the easiest way is just to refer to the graph that you did not make, which is the velocity curve. So what I'm saying is for these 6 questions, which are up here, right in the left corner where I just made that star, right? That is, you're going to use the velocity curve. So I'll write that down as a as the best way to go through this. So use the curve that you didn't make. Use the velocity graph. All right, that'll make your life a lot easier. All right, here's why. If we look at this, when the first question is, when are we moving forward? We're moving forward anytime that the velocity is positive. When are we moving in reverse? Anytime the velocity is negative. When are we stopped? Anytime the velocity is equal to 0. So let's go ahead and grab a highlighter here. Let's get a different color. Let's go, I don't know. I guess we'll stick with the orange. Let's go orange here. So when are we going forward? Well, if I look down at the graph for V versus T, I can see that we're moving forward, or it's the graph is positive, or the velocity is positive from 0 to 58 seconds, right? From 0 to 58 seconds, that's the case. All right, so, well, yeah, okay. So I guess technically at time 0, its velocity is 0. So that would technically be a stop right there. So at time 0, I might want to, I think the best thing to do would be to put a stop line right there. And you can see that in orange right there. And then also at time 58 seconds, right? Which I'm going to follow up from this curve underneath here. If you can see what I'm saying right here, I'm drawing this dotted line. I'm going to follow the 58 up, right? Up through these graphs, right? And draw that line right there. I would not draw that dotted line though through everything, because that'll screw up your other stuff. But that's kind of the logic there, or how I line that up. So those are both 2 stops. But we know everywhere between that, once again, I'm going to grab that orange, and is going to be, whoops, supposed to use the highlighter. It doesn't really matter. I'm going to stick with that. I kind of like, that was a little brighter and easier to see. All right, so anywhere in between there, we're moving forward. All right. And yeah, I can probably do a better job shading and coloring, but whatever. It's all good. Okay. So the next question is, when are we moving in reverse? Well, reverse is going to be after 58, right after we hit that stop at 58. Car is going forward, or the object is going forward up into 58 seconds, and then its velocity becomes negative, which means it's going backwards, right? Or it's going to the left or down or whatever, back, the opposite of what it was doing before. All right, so from 58 to 80, we can now shade in up here. So I'm going to find 58, which is right there, 58 to 80. We're drawing this in right here. And we already did the 2 stops, which are right there at 58 and right there at 0. All right. And hopefully that makes sense. Not too tricky, right? Just use the velocity graph. Okay, let's go ahead and I think that's probably easier for you guys to see zoomed in like that too. So there's my acceleration curve zoomed in, which might help if you couldn't see it well before with my dotted lines that are kind of crummy the way that I drew them, but I usually don't draw those dotted lines. All right, so let's do the last part, speed up and speed down and constant speed. So once again, we're looking at velocity, right? When we're speeding up, our velocity is going away from 0. When we speed down, we have v toward 0. And notice I don't care if it's positive or negative. That does not determine speed up or speed down. I just care, is the velocity going away from 0 or towards 0? And then when the velocity, when it's a constant speed, once again, don't care if it's positive or negative. I just want that we want to hold velocity. We want to keep the same velocity to have constant velocity. All right, so let's get that orange marker again, and let's go back down and look at the graph. All right, so speed up, away from 0. So it looks like from 0 to 20, we're speeding up. From 20 to 30, we're speeding up. From 30 to 40, looks like we're going back towards 0, so that would be a speed down or slow down. So let's go ahead and shade in from 0 to 30 as a speed up. So we're saying up here that speed up is happening from 0. Notice this lines up with the grid underneath there. I try to line it up with the grid underneath it. So this is 30 right there where I stopped shading. And I can try and shade a little bit better. No excuses. All right, so then we said from 30 to 40 that this blue slope, that we're going back towards 0. So that's going to be a slow down or speed down. So we're saying from 30 to 40 right here. Okay. And then from 40 to 50, we're going to hold speed. So that's going to be constant, right? Because we have a constant 20 meters per second on that pink line. Yeah, so we're not accelerating, right? Acceleration is 0, but we're holding speed of 20 meters per second. So that's going to be a constant speed from 40 to 50. Okay, go ahead and shade that in. And then now this is interesting, right? We got to be careful here because we can't say 50 to 70 is all the same. They're actually two different things. Let's think about it. 50 to 58, we're moving towards 0, so speed down. 58 to 70, we're moving away from 0, speed up. All right, hopefully that makes sense. Even though it's a negative acceleration the whole time, in one case from 50 to 58, you have a negative acceleration, and that causes you to slow down in the positive direction. And from 58 to 70, you have a negative acceleration, and that causes you to speed up in the negative direction. All right, that's tricky. So hopefully you can understand what I said there, and that makes sense. If not, maybe rewind it and listen to it again. But once again, negative acceleration can cause you to slow down in the positive direction or speed up in the negative direction. Ooh, all right. Anyways, let's go ahead and bubble those in then. We said from 50 to 58 is a slow down or speed down. Let's see if we can find that. So we're saying 50. Oh, I got my eraser on. All right, we're saying from 50 to 58, which is about right there, right? Notice that 58 time coincides with the maximum of 830 position. All right, and then from 58 to, was it 70? I think it was 70. Yeah, 58 from 70 is a speed up. So we're going to come back up here above and go from 58 to 70. And then finally from 70 to 80, I think that's where we hold speed. Yeah, it's another one of those pink lines. So we're just going to hold speed at negative 30. So we have a constant speed there to end with from 70 to 80. All right, hopefully this is making sense. Once again, let me see if I can zoom out a little bit. Follow these velocity rules that we wrote on the side here, right? And come up with this grid that looks like this here. And so on. That's it. I know on the last test I had a question like this, and I think everything was the same, except sometimes I like to ask multiple choice questions about forward, reverse, stop, speed up, speed down, constant speed. But you were given a velocity versus time graph like the one in the middle. You had to find the areas, draw the position versus time curve like we did in blue here, then go back to the velocity versus time curve, get the slopes and go forward to the acceleration versus time curve, and draw this graph here. And you might say this is a lot. And obviously it is, but the math moves are fairly standard, right? Pretty, math moves that I hope you've been using in your math classes a lot, right? Which is area and slope. And so they're not too complicated to math moves, but it can still be tricky. And you might say, well, how many more of these graphs are we going to make? This is it, just 3. Position versus time, velocity versus time, acceleration versus time. And a tie-in to upper level math with pre-calc and calculus that we talked about derivatives being the slope of the tangent line, that if we had a function for this velocity versus time graph, we could take the derivative to get the acceleration versus time function. If we took the derivative, and we can take the antiderivative with the area from the velocity function to get the position function, and that's called an integral. So there's the tie-in to math class, but you don't have to know that. So anyways, just wanted to point that out. So long story short there is that, area to go back to position versus time, slope to go forward to acceleration versus time, and then to answer these questions about the velocity up above, to answer these questions up above, use the velocity versus time curve, and that's it. All right, we'll do more practice next week. I got at least 2 more graphs like this for us to practice, and hopefully it's all making sense. If not, email me questions or just bring them to class and we'll talk. All right, have a good day.